Welcome back, everybody, to this second part of the series on optimization, where we will continue discussing Adam and specifically dig into the proof. A word of caution: this lecture is math heavy, but we tried our best to make it accessible to everybody. If you happen to have any questions, please write them in the comments below, and we will be more than happy to have a look at them. Before commencing, we would like to thank the community, especially the Reddit community and BioSNN, who figured out a mistake or a typo in our previous lecture, where we were missing a square on the L2 norm, and we corrected that. So thanks for that. We also like the suggestions that we got from Wood SGA2 about the graph, which was just meant to be a parabola. We also thank all people who commented on our YouTube videos, and we would like to mention that the numerator is not wrong to be GT, because the authors will set the beta to be equal to 0, as we will discuss later. And we would like to thank everybody who gave us suggestions to improve the sound in our videos. We definitely will take these into account. We ordered what has been suggested. But give us don't give us such a hard time. This is the first time we record videos, so slowly we will improve. But thanks a lot for that. Cool. So let's do the proof of Adam in this lecture. But let's just recap on what we've done last time. Very quick recap before commencing. So as we said, we're gonna take the NeurIPS 2018 paper, and we're gonna follow their Adam's suggestions as well as the proof. The algorithm itself consisted of these main steps, where in the first step we draw a sample from P, can be your data distribution. We compute the gradient based on the sample we have drawn. Then we compute a vector MT using beta 1 MT minus 1 plus 1 minus beta 1 GT. Now we need to note that the authors in their proof set this beta 1 to be equal to 0, which would allow us to write MT as just GT. So with that MT being GT, we can now update also VT in this way. And then at the end, we can do the update of theta as theta t minus eta t. And as people noted out, this should have been MT. However, because we set beta 1 to 0, this is going to be GT. We took an example last time of regression where we said, okay, the idea here is that we're going to sample some data index, which will give us a loss function on that data index we sample as yit minus f theta x it squared. Then this allows us to compute the gradient GT as shown in this equation. And to compute the gradient, we just use a very simple property where this is a minus b of theta squared, which will be 2a minus b times the gradient of whatever is inside. The gradient of whatever is inside, the first part is 0 because y doesn't depend on theta. And this is the gradient of the f function, which we get here. And that's why we have the minus sign popping up in this equation. With that, we also said that the authors considered a more generic objective function of the form e zeta sampled from pi of some loss theta of xi. And the idea is that this is just a way where you can rewrite most machine learning algorithms or problems in this equation by defining zeta to be a uniform, a random variable, and then we can map regression, for instance, to this objective. And therefore, now we can focus on trying to minimize with respect to theta this objective rather than the specific machine learning objective. And we're going to use Adam to do that. And now with that, we can try to get some generic bounds on the convergence of Adam on this very generic objective function, which then can give us insights into specifics when taking special cases as corollaries for specific machine learning problems. We also made an assumption last time where we said that the loss function is L smooth, which means that the subsampled gradient between two thetas does not change a lot. We gave an illustration on that where we said if you have a theta 1 and that's the gradient, then theta 2, that's the other gradient on that theta 2. The idea is that the change in the gradient should be low, and if that's the case, then the function is L smooth. From that, we were able to show that our function is L smooth, and we commenced from there. Now, what we're going to do in this lecture is we're going to dig deeper into these things and try to do the bounds we would like. So describing a proof is not simple. And what we tried to do is we tried to first give a proof roadmap of what are the main steps needed to achieve the convergence of Adam. And then we're going to take each chunk alone and dig into that. So the first thing we started with was last time, we recap it this time as well, It was that we shown that the objective function is L smooth, and that gave us a relation between two successive iterations. So i.e., because the objective function was L smooth, and we proved that, that allowed me to rewrite that my objective at the next iterate is less than or equal to the objective at the current iterate, theta t, plus something. Now, our goal in this lecture is to bound these somethings, and what are these somethings is what we're going to dig into in a second. However, once we have that, we understand what are the true components that we would like to bound. So this is L theta t plus 1 L theta t. Then it turns out that these are the equations we would like to bound. So we need to bound these equations. Now, unfortunately, these bounds are not so simple, because if I look at this ratio here, GIT over square root of VIT plus delta, it turns out that GIT and VIT are actually random variables which depend on each other, and therefore bounding the ratio is not that simple. So we need to dig into that to do some work. So that's why in the first chunk of the slides, we will be doing the proof or the bound for the first term. We will then be doing the bound for the second term. We will dig in each, so we will continue doing the bound of the first term until we get a bound in terms of the norm of the gradient. Then we will do that for the second term, where we will get a bound in terms of the batch size. After doing that, we're going to replace these back in the original bound and start choosing some parameters which will allow me to complete my proof. So this is the overall roadmap of what we're going to do. As we said, we start from L smoothness. Then we understand what components we want to bound. We bound each of the first term and the second term. We get some bounds in terms of the norm of the gradient and the batch size. We then stick it back in the original bound, choose parameters, and get our final result. So let's dig into these. So as we said last time, as in any other optimization problem, in order to prove convergence of Adam, we need to study the change of the function value between two successive iterations. And we would like to get a result that looks like this. We would like to say f theta t plus 1 is less than f theta minus some delta, where delta is some positive value. Because the function is lower bounded, then this thing should converge. So therefore, if we can say that the objective function is L smooth, then we can find a relation between two successive iterations of the objective at theta t plus 1 and the objective at theta t. So we did this last time. We're just recapping this while fixing the mistake that was pointed out. And the idea is that we will prove in a second that the loss function is L smooth. And because it is L smooth, then we can write L theta t plus 1 is less than L theta t, which already gives us the relation between two successive iterations that we were looking for, plus the inner product of the gradient and this vector theta t plus 1 minus theta t, plus L over 2 times the norm of theta t plus 1 minus theta t squared. So that's what we were missing last time. The squared should have been there. Apologies for that typo. So now, as you see, what we really need to do is we really need to start bounding this and this in terms of something that will allow me to say some convergence property about the Adam. So let's start doing that. So, right, so sorry, before doing that, we just showed again last time that the function is L smooth. The proof was simple. We just started with the completed gradient, which we wrote as the expectation of the loss. We worked through the properties of expectation, and that allowed me to say that using the assumption that my function is L smooth, therefore the upper inequality holds. Good. So I believe that's where we reached to last time, and now we're going to take it from there. So as we just proved this is the case, so we can write our objective function in this way. And now we remember our update rule from the pseudocode. So the update rule of MT looks like this. As we said before, the authors choose beta 1 to be 0, which gives me MT to be GT, and therefore my update theta t plus 1 becomes theta t minus eta GT over square root of VT plus delta. So now we take this equation and then we start plugging it inside this bound here. So to do that, we realize that if this is a vectorized way of updating the parameters, then the component update can be written in this way, and that's really simple. It's just that the ith component at t plus 1 is the ith component at t minus this learning rate eta t times the ith part of the gradient and the ith part of the v vector. So then we take it, plug it in this, and then we realize that we can write this equation in this way, where we have the loss function at theta t plus 1 is less than the loss function of t minus summation from 1 to d of the ith component of the gradient of the objective times git divided by square root of vit plus delta, which is nothing but this equation here. So all we've done really is just took this and substitute here and did this inner product, plus L eta t over 2, eta t squared over 2, then times the summation of git squared over this squared. Why this comes? Well, simply because we're going to substitute theta t plus 1 minus theta t from this equation here, which is nothing but eta t gt over square root vt plus delta all squared. And that's why eta t becomes eta t squared, and then the inner part is just the norm of the gradient squared, which is nothing but the summation over all of the components squared, and similarly for the denominator. So all we've done here was simply just plug in the update rule in this L smoothness bound we got, and then that gave us this equation. So now what is our goal, right? So our goal is to try to understand what will happen throughout the process of applying this Adam iterative rule. Now we need to note, however, that Adam is a stochastic algorithm and not a deterministic algorithm. Remember, at every step of Adam, at every iteration t, we sample some xi t, right? Now that makes the process stochastic and not deterministic. So this equation here is not right to be written without taking into account some stochasticity. And that's why, in order to do that, we're just going to take the expectation on both sides of this equation given the random variable θt. So given that we know what happened in θt, what can we say about the expectation of change in the objective function? So to do that, we just plug in the expectation. That gives me this equation. Let's go slowly through this equation. So remember, all I'm going to try to do is I'm just going to try to put this expectation of the objective conditioned on theta t on both sides of this bound. So on this side, well, we leave it expectation of objective at theta t plus 1 given theta t. Less than or equal. Now, of course, here you would say, well, we need to have an expectation of that objective of theta t, L of theta t given theta t. Yes, you're right. However, this is not stochastic with respect to theta t, because we know theta t, so this objective at theta t, L of theta t, is actually deterministic. And that's why we can get rid of the conditional expectation on L of theta t. Now we similarly take the expectation of the second term. So you will have expectation of minus eta t summation from I equals 1 to d of this ith component of the gradient of the objective times this git divided by square root of vit plus delta. Okay, now we know that e of a constant times something is just that constant times something, and that's why eta t can go out of that expectation, and that's why you see it here. And we also know that e of the summation is nothing but the sum of the e's, and that's why we can take e inside this component. So now we have e of this product, the gradient of L theta t I, times this git divided by square root of vit plus delta. Well, now notice again that conditioned on theta t, this is known. And that's why this is not random, and that's why it's like a constant. So it goes out of the expectation again, and we're left with the expectation of git over square root of vit plus delta. Then we do the same thing here. So we still have an expectation here. And now again, that's a constant, so it goes out. E of sum is sum of e's, and then we have just e of git squared over square root of vit plus delta squared given theta t. So what we've done effectively here is just simply said that Adam is a stochastic, so we should be careful. We shouldn't consider it as a deterministic proof. We should in fact consider it as some notion of stochastic proof. So let's try to prove things in expectation. However, the expectation has to be conditioned on what we know now, and that's why we took a conditional expectation. Now, some might argue this is a random variable, and that's true. So this conditional expectation itself is a random variable. At the end of the proof, we will take the total expectation, and by the law of total expectation, this will go away. We will see that in a second. But now what I want you to understand is that the simple thing we've done here is we've just taken this expectation on both sides given the knowledge of theta t. And then we played with the expectation properties that allowed me to rewrite the equation in this way. Good. So now, so as we discussed, this is fully known, this is fully known, these are dependent random variables, and so forth. So therefore, as you see from our proof roadmap, we reached a place where we went from the objective function being L smooth to understanding what are the true components that we need to bound. So we saw there's this ratio of dependent random variables, GIT over square root of VIT, and we also saw that there's this chunk that we need to consider. So now what we will do is we will start bounding these. Right. So now we are faced with a very big question, really, because you see, let's look at this term here, right? So this term has a ratio of random variable GIT over square root of VIT. The problem, however, is that these random variables are dependent on each other. So it's not like this is an independent random variables, because if that was the case, then I can split this expectation with respect to this ratio. But the problem here is that these random variables are dependent, so we have to have a smart way to deal with this, because otherwise we cannot bound this term. So here's how the authors dealt with it, and that was actually a very smart thing they've done. So they took this equation, so this is the equation you see above, but now what they did, so this is just L is here, eta t summation is here, gradient is here, now you have this E is here, and this term, L eta 2 over 2, L eta squared over 2, blah, 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 stays here. Now what the authors did, they added and subtracted this term. Now, after adding and subtracting this term, we will be able to get rid of this ratio problem, but keep that in mind because we're going to see it in a second. But just keep in mind that the reason they're adding this term and subtracting it is that later on it will help me get rid of this ratio problem. So what are these terms? They added GIT over square root of beta 2 VIT minus 1 plus delta, and added the same GIT square root of beta 2 VIT minus 1 plus delta. Of course, these are the same terms, so adding, subtracting means 0, so that equation is not changed. And now you might have a glimpse on what's going on, really, because remember, there is some relation between VIT and VIT minus 1, right? We're going to exploit that in a second, and that's what we're going to allow me, to deal with this ratio. But for now, all we've done is, because we want to handle a ratio of dependent random variables, what we did is we added and subtracted this term. So now after adding and subtracting this term, what are we going to do with this expectation, right? Because now remember, we have E of sum A minus B plus C. Okay, well, the way we're going to deal with that is we're going to use a property of expectation which says that E of A minus B plus C can be written of E of A minus B plus E of C. Well, we know that the expectation is additive, right? And then you can just add and subtract the expectation normally, and that will give me this. So therefore, I apply this here, and that will give me the following. So I will have E of A minus B, which is E of GIT over square root of VIT plus delta, minus GIT over square root of beta 2 VIT minus 1 plus delta. That's this, E of A minus B. And then don't forget, we have E of C, and therefore we get here plus E of C, which is nothing but E of GIT over square root of beta 2 VIT minus 1 plus delta given theta. So all I've done here is I just applied this simple property of expectation to the added addition and subtraction that I just did in the previous slide. So now it's interesting to realize here that given theta t, the denominator of this equation is fully known, right? Because this depends on t minus 1. So it's like square root of beta 2 VIT minus 1 plus delta. So this is fully known. It's not really random. It's like a constant. And that's why I can take this outside of the expectation and have it not conditioned on anything because it's fully known. And therefore, it's like E of 1 over some constant times GIT given theta t, which is nothing but 1 over that constant, that's what you see here, times E of GIT given theta t. So here, I've just used the fact that the denominator is independent of theta t, and that's why I can rewrite this in this way. But now what is E of GIT given theta t? Well, we know that, right? Because we have an unbiased estimator. So the expected subsampled gradient is nothing but the gradient. And that's why the GIT should, or like the whole vector G in expectation should give me the whole gradient of the objective. And now therefore the ith component of that is just the ith component of that gradient. Right, so I think there is just a minor typo here. This should have been theta t actually instead of theta, but this holds for any theta, so that's all right. But it's just this should have been theta t because we're just studying GIT, so i.e. at theta t. But the idea here is that you have this E over GIT given theta t will give me nothing but the ith component of the gradient, and the denominator does not depend on theta t. That's why I can take it out. Good. So now what we're gonna do is we are gonna take this equation and then put it back in here. So E of A minus B remains unchanged. That's what you see here, right? And therefore, and E of C, so plus E of C, and that's what you see here. So what we did effectively is we took, right, so let me recap just to better understand this. So remember, this was our original equation. Then we started dealing with this term here, where we said, okay, this is EA minus B plus C, which is EA minus B plus E of C. And now E of C happened to be gradient over square root of beta 2 VIT. And that's why this multiplied by this plus this minus that. So this is what we just saw here. So the idea of what we just saw here is nothing but you take E of A minus B here, E of C here, that is multiplied by the gradient, don't forget that, because that's from the original bound, and then we have this term unchanged. Good. So now let's go on. Right, so yes, so exactly. So what we're trying to say here is that you just substituted this here, we substituted that there. Good. So now let's continue, and we're just gonna do a simple product now. So we're gonna take this term multiplied by this term, which will give me just the gradient of the objective I squared. And we're gonna take this term multiplied by this term, which will give me nothing but the gradient I squared multiplied by this expectation. So this is like, think about it as a constant of A plus B. So that's like kind of a constant times A, which gives me that. And that's like a constant times B, which gives me that. So this is nothing but the product of this gradient I into each of these terms here. Right. And now I just take this and plug it back into my previous equation. And that will give me this squared divided by square root of beta 2 VIT minus 1 plus delta plus this chunk here. So we got this, put it there. We got this, put it there. And now we can also split the sum, right? Because this is sum of A plus B, like sum of something plus something else, which will allow me now, because of this sum, to write it as a summation of two things. So it'll be sum of that guy, that's what you see here. And then you have sum of this, which is what you see there, right? So again, what we've done is just took this, made the multiplication. After we made the multiplication, we are able to split the sum because that's just an addition here, and that allowed us to do this. Good. Right. So now what we need to do is we need to start somehow playing with these terms in order to get our delta. Remember, the f of xt plus 1 minus f of xt should be less than sum minus delta, where delta is positive, right? So now we are still trying to go in that direction, really. And notice that this is okay. I mean, this is great because you see, you got here the gradient of the objective squared, the gradient of the objective ith component squared, which resembles kind of the norm of the gradient, which is good because that's a positive thing. But now what are we going to do with these things here? Because also we would like to bound these such that we get just something in terms of the norm of the gradient, which is a positive thing, and that's good. So what we do here is we use the following property. We know that the absolute value of sum eta t summation from I equals 1 to the ai bi should be less than the eta t summation I equals 1 to d of the product of absolute values. And we know that this is greater than the negative of eta t summation of ai bi. So therefore, negative of eta t summation of ai bi can be written as less than the eta t summation I of the product of the absolute values. So what we're going to do is we're going to apply this right here. So see, we have minus eta t, so that's this thing here. We have summation I equals 1 to d, that's this thing here. Gradient of the objective I is nothing but ai. E of that whole thing is nothing but bi. And now I can write it in this way. I can write it as less than eta t summation of the product of absolute values. So that's exactly what we just said, right? So this is ai, this is bi, and then that allows me to rewrite this. So with this, I just rewrite using this equation, and I can say this is less than eta t summation I1 to d of the gradient, absolute value of the ith component of the gradient times the absolute value of b, which is this monster right here. Good. So therefore now this remains not changed, right? So I'm just gonna now take this, plug it in the boundary, that's all I'm gonna do. And that's why we have a less than, because remember this is an inequality here, so it's not equal anymore, it's gonna be less than. I'm gonna take this, put it here, and that remains unchanged. So all we've done is in our original bound, we kept this the same right there. And we use this property of the absolute values here, which is like the triangle inequality. That allowed me to rewrite this, and that allowed me to rewrite that as being unchanged. What we're gonna do now is we're gonna dig deeper into this and try to bound this. Right. So we have the absolute value of E of this GIT over square root VIT plus delta minus GIT of square root of beta 2 VIT minus 1 plus delta given theta t. And we know that the absolute value of E of x is less than or equal to E of absolute value of x. And I mean, this is easy to prove. Maybe you can practice that. This is like, maybe just take that as an exercise, how to prove this, but this is easy to prove. And then what we can do is we can just apply this property here, which will allow me to rewrite the absolute value of E as less than E of the absolute values. And now we're just gonna focus on this term right here. So let's call this term T1, right? And T1, as you see here, is nothing but GIT over square root VIT plus delta, which is this, and minus, which is that, GIT over square root of beta 2 VIT minus 1 plus delta, which is nothing but this. So now what we can do is, as you see here, we can take GIT as a common factor. So that will be absolute value of GIT multiplied by 1 over this denominator minus 1 over that denominator. Now by the property of absolute values, this is a product of absolute values, which is equal to the absolute value product. Therefore, we can now just write this as the absolute value of GIT outside multiplied by the absolute value of the 1 over the first term here minus 1 over the second term right there. So all we've done is just took a GIT common factor and used the property of the absolute value. Now we take a common denominator, right? So now you have like two fractions, 1 over A minus 1 over B. And I just want to be able to like multiply and or just make this addition. Then I just take a common denominator, which is just the product of the denominators, which is just the square root of VIT plus delta times the square root of beta 2 VIT plus VIT minus 1 plus delta. And then I just do a cross multiply. And once I do cross multiply, so this becomes here. So that would be square root of beta 2 VIT minus 1 plus delta minus VIT minus delta plus delta minus delta cancel out. And then you're left with the term of square root of beta 2 VIT minus 1 and square root of VIT. And of course, the common denominator is positive, so it just goes out without the absolute value. And please notice that these are flipped, right? Because we just said that we should have beta 2 VIT minus 1 minus VIT, but it's absolute value, right? So you can flip it again and there's no problem there. Good. So now we're focusing on this term, which popped up in our bound, and we just used some properties of absolute value here in order to write it as a multiplication. Then we took a common denominator that gave us this specific thing, right? Now we're gonna use some property again about square roots and absolute values, which says that the square root of absolute value of square root of A minus square root of B is equal to absolute value of A minus B over square root of A plus square root of B. Right, so now this might sound really weird, but like it's easy to prove, right? So to prove that, you can start by writing that A minus B can be written as square root of A minus square root of B times square root of a plus square root of b. That's why we get this term here. That's why we get this term here. That's why we get this term there. And then, of course, take the absolute value, reorder your equation, you get just this equation. So now we're going to apply this equation just right here. And we're going to say, okay, so square root of a minus square root of b. So that's this. So absolute value. Square root of a is square root of VIT. And square root of b is square root of beta 2 VIT minus 1. So once we apply this here, we will get absolute value of a, which is nothing but VIT, of b, which is nothing but beta 2 VIT minus 1. And that all is divided by square root of a plus square root of b, which is just the square root of VIT plus the square root of beta 2 VIT minus 1. So we have this, and all we've done here is just use this property right there. Good. So now let's continue with this equation. And now remember that our original update rule for VIT was written in this way. So it was written as beta 2 VIT minus 1 plus 1 minus beta 2 GIT squared. So where does this come from? Well, this just comes from the update rule of the algorithm itself. What we're going to do now is we're going to take, instead of VIT, and plug in this equation instead of this VIT. So we arrived here, if you recall, right? So that was the place where we arrived. And now what we're going to do is we're going to take the equation of VIT from our algorithm and then plug it in. So upon plugging this in, then we can arrive to this equation right here. So it's really simple. What we've done is just that we took this VIT equation from the original algorithm, and then based on that, we plugged it in, and that gives me this equation. So with that, now what to do is we again remember that the VIT is again this same equation, so we plug it in again. And after we plug it in again, we arrive to this equation. So all I've done from getting from this equation, which we just saw here, to this equation, which we saw there, right, is nothing but plugging in the update rule from our algorithm. I mean, so far, as you realize, we have been more or less generic about the update rules. But now, in order to understand what happens with Adam, we need to start plugging in the update rules from our algorithm. And that's exactly what we've done. So we just took this, plugged it in, and that's what we get. Good. So now we arrive to this term, and then we ask the question, now what? Okay, so now we have to deal with this somehow, and how are we gonna do that? So let's see. Right, so let me recap till now what we've done. So it's we just proved that the function is L smooth. After we proved that the function is L smooth, we plugged in the equations from the update rule of theta. We got this dependent ratio of random variables. Once we got that, we added and subtracted a term to get rid of that. Then we continued bounding each of the terms, and then we arrived to here. Good. Right. So now, what are we going to do? So this is the equation which we had here, right? So now we want to try to deal with that equation. In order to do that, we now remember a property about a fraction. So it's easy to see that 1 over a plus b is less than 1 over a if a is positive and b is greater than or equal to 0. So this is easy to see, right? Because you're just doing 1 over some number plus some positive number. And that's just nothing but less than 1 over that number without the addition. So now, because this square root of beta 2 VIT minus 1 is non-negative, then I can apply this property to this equation and get this, right? So all I did is I took this property here, and then a plus b, this is a, this is b. So I have 1 over a plus b, which is nothing but less than or equal 1 over a. And that's why we have less than or equal. This part remains the same. This part remains the same. But now we just do 1 over a, and that's this part here. So that's our a, that's our b, and we just use this in order to do 1 over a. Good. Now, we also say or remember that square root of a plus b is bigger than square root of b if b is positive and a is greater than or equal to 0, which implies that 1 over square root of a plus b is nothing but less than or equal to 1 over square root of b. And therefore, if I take this to be a and b, and then I just apply this again, then I will get this equation. So let's look at this equation. The less than stays less than, so that's less than here. This term remains unchanged, as you see. This term remains unchanged, as you see. And now we just said that square root of a plus b, or 1 over square root of a plus b, is less than or equal to 1 over square root of b. And that is why we have 1 over square root of 1 minus beta 2 GIT squared. So now this is pretty cool because you see, we got a lot of GITs and the square root of 1 minus beta 2 and so on. So we can really simplify this equation. So for example, we know that if you take GI2 squared outside of the square root, you get absolute value. Then that makes this and this cancel, right? And then 1 minus beta 2 divided by square root of 1 minus beta 2 can also simplify because this is like to the power 1 minus half. So then you just get in the numerator a square root of 1 minus beta 2. So now what we're going to do is again, right? So remember why we're doing this, because we started focusing on this and we dove into this bound and then we arrived here and now we're continuing our bound. Good. Right. So now I just will do what I just said in order to get this equation, right? So I just removed, so I took GI2 squared from the absolute value. That takes this away. Then you have 1 minus beta 2 to the power 1 over 1 minus beta 2 to the power half, which is just 1 minus beta 2 to the power half. And that's why you get this. So now we are getting this equation. And we're going to use the same trick we used before, where 1 over a plus b is less than 1 over a. Of course, for a positive and b greater than or equals 0. And now we're going to take this as b and this as a, apply this equation, which will give me the following bound. So it'll give me T1 to be less than or equal square root of 1 minus beta 2 GIT squared over delta square root of beta 2 VIT minus 1 plus delta. So you might wonder where this delta came from. Remember, we're going to do 1 over a plus b is less than 1 over a. So 1 over delta plus VIT is just going to be less than 1 over delta. And that's where this delta pops up from. Good. So now we take this and plug it back in our original bound, and then we can get some nice equation about this first term, but we didn't finish, right? We're just halfway through. Good. Right, so I take this equation I just got, plug it back instead of T1, which was this term here, and that would give me now the equation that looks like this. So it'll be whatever we had here. We had like L theta and we had here L eta over 2 squared and so forth, but let's ignore that for now because we're just focusing on this chunk. So then you will get eta t summation I equals 1 to d. Remember, we had the absolute value of the ith component of the gradient multiplied by e of this absolute value, right? And now we said that this is T1 and we bounded T1 in this way, right? So we bounded T1 in this way. So now I plug the T1 in here and now I will have e of the T1 conditioned on theta t because we called this absolute value just T1 and now we have e of T1 conditioned on theta t. So now what happens is that I just plug this in here and therefore I will get eta t summation 1 to d, the ith component of the absolute value of the gradient, times the square root of 1 minus beta 2 e of GIT squared given theta t over delta square root of beta 2 VIT plus VIT minus 1 plus delta. So what happened? I just plugged this equation in its place in the original bound and I get here. Good. So therefore, now the overall bound will look like this, right? So our overall bound is that the conditional expectation of the objective at theta t plus 1 is less than or equal to the objective at theta t. This term was before here, doesn't change, and we said that's good because it has something related to the norm of the gradient. This term here we just shown, this term here does not change. So this is from before. And now we need to, I mean, we're getting there because like we started seeing like GIT squared and that's pretty good. And now if we can somehow have a gradient here, then maybe we get gradient squared and these terms can become like the norm together. So let's see how that all that is done. Good. Right. So now what we're gonna do is we're gonna introduce one more assumption to be able to handle this, the absolute value of the gradient. And that assumption says that the loss function has bounded gradients. I mean, it's not a restrictive assumption really. It just says that anytime you take the gradient, that norm of the gradient is bounded by some g, right? For any randomness you have xi. With that, we can say that the norm of the objective, so again, remember, this is the same problem as the L smoothness. We showed that, or the assumption was that the subsampled is L smooth, but we needed to show that the original function is L smooth. Here is a similar problem which says that the subsampled gradient is bounded, but now we need to show that the gradient of the objective is bounded. And that's again very easy to show. Well, the only thing, or what we're going to do is again start from the norm of the gradient, and then that will be just the expected of the loss function. So that's the gradient of the objective, and this will be the and the loss function is nothing but e of the the objective is nothing but e of the loss function, and that's why now e of the gradient comes in here. Now you use the property that that the norm of e of x is less than e of the norm of x, and now here comes in this assumption which makes it less than g, and if the norm is less than g, then every component of that vector is less than g as well. And now we can plug this in here. Good. Right, so now as you see, all we've done is just plugged in, instead of the absolute value, this from this assumption, and then we took it outside of the summation because it's like a constant now. It doesn't depend on I, right? So once I plug this in here, there's no dependency on I. So that's like multiplying the same constant by a plus ai. So constant by a1 plus constant by a2 plus constant by an, which is nothing but the constant times the summation. And that's just what we see here. So what we've done is taken out all the constant. This includes the g and also delta, and the square root of 1 minus beta 2. Good? Easy, right? So we reached here, we made an assumption, then we took all the constant outside, and that allows me to write it in this way. Now let's focus on the second term. So we dealt a bit with the first term, which allowed me to simplify my bound from a horrible looking bound to a less horrible looking bound. And now there still needs to be some work on this, but we will get to that in a second. So now let's focus on this equation for a little bit. So as you see, what we've done here is we've bounded the first term now, and now we're gonna try to use that plus the bound of the second term in order to choose parameters. So now we're kind of here, but we still need this guy to pop up. Right, so now what we're gonna do is we're gonna bound the third term, right? So that's our focus now. And in order to do that, we again start by plugging in our equation, our update rule from our algorithm. So we plug in the update rule from our algorithm. So instead of VIT, we just replace it by beta 2 VIT minus 1 plus 1 minus beta 2 GIT squared. And now that gives me this equation here, right? So if you look at the denominator, instead of square root of VIT, we just have square root of VIT minus 1 plus 1 minus beta 2 GIT squared plus delta all squared. Simply plugging this in side of VIT. Now with that, we again play the same trick we did before, right? So we realize that this is non-negative, and if this is non-negative, right, we can bound this as we did before. So the bound will look like GIT squared over square root, so less than, of course, there should be a less than here. So this is less than GIT squared over square root of beta 2 VIT minus 1 plus delta all squared. So what we've done is, again, just use the fact that 1 over square root of A plus B will be less than 1 over square root of A, and that's A and that's B. So now we take this, plug it back inside our original bound. Remember, this is the original bound. It's nothing but the loss function at theta t plus 1, and that's the loss function at theta t. That's what we had before. This is after we introduced our assumption and took out of the summation the constants, and now this is what we get. Now this is pretty cool, right? Because what you see here is that GIT squared and GIT squared are popping up together, right? And we also have very close denominators, but this is something squared. So let's see what we can do. Can we do something with that? Right. So what we're gonna do, so this is just something we just plugged in from before, right? And now what we're gonna do is we can further bound this actually. And the way we are gonna bound this is in a similar fashion like we did before. So that is gonna give me the L eta t squared over 2 of the summation of E of GIT squared over square root of beta 2 VIT plus 1 plus delta squared. It's gonna be less than 1 over delta times that times the summation of whatever we had before. So that's what you see here. Good. So now we have the same denominator. So remember, I told you before in this equation that these are so similar, but the denominators just have this different power, right? This squared power. So can we do something with that? Well, with this bound, what we were able to do is that we were able now to have the same denominator. But that's good, because now with the same denominator, we can actually sum these up and just do some bound on that. So now what you have is you have eta t g square root of 1 minus beta 2 over delta summation of e of git squared over square root of beta 2 vit minus 1 plus delta. And now remember, plus L eta t squared over 2 summation of this thing right here. So now you can take this as a common factor. So you can take e of git squared over square root of beta 2 vit minus 1 plus delta as a common factor. And you can take the constants outside of the summation. You get this equation, right? So in order to make sure, just multiply this equation. So if I multiply this equation, I'll get eta t g square root of 1 minus beta 2 over delta times this sum, which is this first part here, plus L eta t squared over 2 delta multiplied by this sum, which is this part right here. Right? All good. Great. Now we're gonna again use the same trick we used before, where now you have 1 over something like an a plus something, a which is positive plus b. And now what we're gonna do is we're gonna write that less than 1 over b. So this is a, this is b, so that would be less than, that constant stays there, nothing changes here. Summation is here, and now we just bound it by 1 over delta, and therefore now we have e git squared given theta t. So therefore this is equal to 1 over delta, because we can take the 1 over delta outside of the summation sign, 1 over delta this equation, summation I1 to d e of git squared. Now remember that this here is nothing but the norm squared, right? Because this is just summing each component squared of the vector g. So that's kind of like the e of the norm squared. Good. Now, why is it e of the norm squared? Again, remember, e, you can take it out of the summation. So it'll be e of the summation. And that summation squared is nothing but the norm. Great. So now what we're gonna do is we're gonna start trying to bound this term right here in terms of our g that we introduced before. So remember, what we did is we introduced a upper bound on the absolute value of the gradient. So not to do additional assumptions in order to bound this denominator here, can we somehow use the update rule in order to do this bound? Well, yes. So what we can say is that a VIT is less than g squared for every I and t, and that would say that beta 2, square root of beta 2 VIT minus 1 plus delta is less than square root of beta 2 plus g plus delta. So why is this the case? Again, just plug in the update rule, you would see it. That's like not hard to see really. It's just like plugging in the update rule and then you will be able to see that. Good. So now we can, instead of this denominator right here, we can now put this equation. So that would be minus eta t summation I equals 1 to d of the ith component squared divided by this denominator, which is just this term right here. That is less than this times that, which is what we just shown here. So this term comes from this bound, and this stays there, right? So this stays there. And now, as you see, this is minus eta t over square root of bg plus delta multiplied by the norm of the gradient of the objective squared. So this is good because now we have the gradient, the norm of the gradient of the objective, which is a positive term, right? So that's good. Remember, we wanted to get this less than this minus some positive delta, right? So we're getting close to that because this is our positive delta, because the gradient is always positive delta because it's a positive number. And then you have this minus with some constants, which we need to choose later. Right, so now I just plug this back in, and now what will happen is this bound will look like this. So this equation, once you take from here, there, you get here, and then this term remains untouched. Okay, good. And remember why we got here the norm, because we had summation of e of git squared, which is e of summation of git squared, which is nothing but the norm of gt squared. Good. So as I said, this is some positive term, which is fantastic. And now let's see what we can do with this term here. So in order to deal with this term, we're going to now introduce an assumption. Yeah, more assumptions, but yeah, we're going to introduce that assumption to be able to handle this. So the assumption would say that the variance of the objective is bounded. Sorry, of the loss, not objective, of the loss is bounded, which means that the E of the norm of the gradient of the loss minus the gradient of the objective is less than sigma squared. And now with that, you can actually show that if you have a mini batch BT subsampling of GT, you can actually show that this is true. So you can show that E of the norm of GT squared is less than 1 over BT sigma squared plus the norm of the gradient of the objective squared. Now the thing is this proof is not so simple, but it's also not so hard. So what we decided to do, rather than proving it, we decided to give it as an exercise to you. So give it a shot, right? Like try to see how you can go from this to this and see how we can prove that. Again, like write these answers in the comments and then we will have a look at them and we can have discussions over them. And also if you would like to have more questions, again, write it in the comments or we can have a live session. We're gonna do a poll on that later. But the idea is that it's not so hard to go from here to here. But now, once we go from here to here by introducing this third assumption, now we can plug this equation back there. So yeah, can you prove it? Like give it a shot. Right. So now where are we? Remember, we had L smoothness. We went to components bounds. We bounded the first term. We bounded the second term. And we dug into these to bound them. Now we need to substitute back and choose parameters. So let's do that. So now, accumulating everything we have done so far, we are able to say that E of the objective at theta t plus 1 given theta t is less than the loss at theta t minus this constant, as you see here, if eta t is constant, and times the norm of the gradient squared, plus another constant right here, times something about the norm of the gradient square, multiplied by something of the bound of the variance, and a batch size that is time dependent. It turns out it's very crucial to have a batch size that is time dependent, as we will show in a second. Right, so now what we can do is we can just multiply this by the norm of the gradient, then take the norm of the gradient as a common factor, which allows me to rewrite it in this way. So, okay, let's check that. It might be not easy to see. Let's multiply this equation. So if I multiply this equation, I will get eta t square root of beta 2g plus delta times the norm of the gradient squared, which is just this term here. And then if I multiply this by this, I will get nothing but the plus of 1 over delta eta t, this term 1 over beta t, times the gradient norm squared, which is nothing but, oopsie, sorry for that, which is nothing but this term right here multiplied by the norm of the gradient. So yeah, sorry for that. So again, this is nothing but this times that, which is that, and then it's this times that, which is just this component times that component, and then the remaining term is nothing but 1 over beta t times that term times sigma squared. So that's what we see right here. Good. We're getting there. I promise we're getting there. I know it's a long mathematical derivation, but we're getting there. Now we are at the last part of the proof, hooray. And in the last part, what we need to do is we need to start choosing constants. So as you see, we have control over beta 2, we have control over eta t, and we have control over delta, and also the bt, like the batch size. And now what we're gonna do is we're gonna start choosing these constants somehow in order to allow this to go to 0 and this to be a positive times the norm of the gradient. Because with that, we will get an equation that looks like this, where this will be a positive constant, and that's what we wanted before, as you remember, and the constant ct, which we wanted to go to 0, and if that happens, the function is lower bounded, we have convergence. Great. So let's start choosing these three parameters, batch sizes, learning rates, and so on, to get what we want. So we are free to do that. Let's see how. So there are three things we will choose. The first thing we will choose is the batch size. We will also choose the learning rate, and we will also choose the free parameter beta 2. So in order to do that, right? So let's just this is the same equation as you saw before. We just collected the gradients together, and we collected the batch times sigma squared together. So let's start with this term, which we call A. Now choosing beta t to be greater than 1. And now, of course, this is not choosing. It should be like because, right? I mean, it's of course that the batch size is greater than 1. So if the batch size is greater than 1, then we can say that 1 over delta bt times this term here is less than 1 over delta times the same term here. Why? Because bt is greater than 1. So it's like 1 over delta times something greater than 1 is less than just 1 over delta because you're dividing, right? So it's less than 1 over delta times this term here. Now that will allow me to say, remember we have here minus 1 over delta, right? So this guy here is just this guy here, right? So now that would be minus 1 over delta beta t, which is greater than minus 1 over delta times this thing right here. With that, we can say that A is nothing but greater than eta t 1 over square root of beta 2g plus delta minus 1 over delta g square root of 1 minus beta d over delta plus L eta over 2 delta, okay? So where did this come from? Well, simple. You see this part is in A, but without the eta t over square root of beta g plus delta. So you can add on both sides eta t over square root of b2g plus delta. So you'll get that term here and you will get it here. Now, if you take eta t as a common factor, you just get this equation. So with beta t being bigger than 1, we can say that eta t is greater than this term right here. So A, sorry, can be greater than this term right here. Good. So now let's continue by calling this B, and let's bound that. So right, so we want this B. Now what we're gonna do, and that's what the authors did in their paper. Maybe that's not so practical, but that's what has been done. We're gonna choose eta t to be a constant, right? So eta 1 is equal to eta 2 is equal to eta t is equal to eta, so it's a constant, and we're gonna choose it such that L eta over 2 delta is less than g square root of 1 minus beta 2 over delta, right? So what that will allow me to do is it will allow me to bound this term right here, really. Because see, these guys here are g square root of 1 minus beta 2 over delta, and then L eta over 2 delta, and doesn't have t because we chose it as a constant. If we have that, so if we choose eta t to be less than this, then we can say something about this term and therefore about b altogether. Now, please notice that from this you can get eta, right? That's easy. You know, we just cross multiply, deltas cancel out, 2g comes here, divide by L, you get eta. And that's what this equation says, right? Good. So now with that, what we can say is that g of square root of 1 minus beta 2 over delta plus L eta over 2 delta is less than 2g square root of 1 minus beta 2 over delta. And therefore, minus that is greater than minus 2g square root of 1 minus beta 2 over delta. Why is that the case? Because we just multiplied by negative, and that means we flip the sign, right? We multiply by negative, we flip the sign. And then that will allow me now to say that my b, so this term here, is greater than 1 over square root of beta 2 plus g, g plus delta, minus 2g square root of 1 minus beta 2 over delta squared. So why is that the case? It's again the same story as before. We were able to have a bound on this, and then we divide it by delta, and then we add this term, then you get this equation. Good? All right. So now we chose the batch size, we chose the learning rate, and the last thing we need to choose is the free parameter beta 2. What we're gonna do now is we're gonna choose beta 2 such that 2g square root of 1 minus beta 2 over delta squared is less than 1 over 1 over square root of beta 2g plus delta. Now what that will allow us to do, so if we choose beta 2 such that this is equal to half of that, then this will be satisfied really. Then we can say that beta 2, so we solve this equation, is 1 minus delta to the power 4 over 16g squared g plus delta. Now this is interesting, right? Because what do you choose beta 2 in practice? If I recall, beta 2, you choose it to be very close to 1, right? So you choose that to be 0.9999999 something, right? So now if we look at this equation here, really, this is a very small number. Remember delta, what is delta? Delta is our parameter that we added to avoid numerical instability. So that's something like 10 to the power minus 8 or something, right? That's a very small number we add, which means this is almost 0, not quite, but almost 0. And therefore beta 2 is going to be 1 minus something very, very small, which will be like very close to 1. And that's why what you do in your experiments is you choose beta 2 to be very, 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 very close to 1. And that seems to work. So it's interesting because if you change that, the algorithm doesn't work as well. And it turns out that mathematically there was also a reason for that, and that's the reason here. Of course, you might argue that beta 1 has been chosen to be 0. That's correct, but as we said before, Rasul and I have fixed that, and it's not a hard fix to do. We can show you that later. That's fine. But as you see now, we got from the math, which is great, something that people use empirically, which is beta 2 is going to be very close to 1. And that's good. That's nice. Right. So with that, we have beta is greater than, B is greater than 1 over 2 square root of bg plus delta, which implies A is greater than eta B, which implies that minus A is less than this term. Okay, how do you get this? Just play with the equations a bit. It's really simple to do this. Just plug in the results we got here, back in the equations above for B right there. So if you plug them back here, then you would get this equation we have here. Sorry. Yeah. And now with that, we just use these bounds back in our original equation, which will allow me now to simplify this bound right here. And that leaves me to deal with this constant right there. So right, so this is this minus, that's just that. So now I can plug this in here. And now I'm still left with this to deal with, which we call C. Right, so now let's plug that in and let's deal with C. So remember, to deal with C, you cannot anymore arbitrarily start choosing parameters. Why? Because you cannot conflict the parameters we just chose before. So now we keep in mind that we made a choice of eta t such that this is true. But because this is true, now we can directly say that C is less than 2 eta g of square root 1 minus beta 2 over delta. Why is this the case? Easy, right? Because take eta t as a common factor here and set it to a constant. Then you will get here g square root of 1 minus beta 2 delta, which is this term here. And then you get here L over 2 delta, eta t, because we took 1 eta here. And now you can apply this in order to get here. Good. So now putting everything we did together, now the equation is becoming much simpler. So we have the bound saying that the loss or the objective at theta t plus 1 is less than L of theta t minus the norm of the gradient squared, which is just a positive thing, multiplied by 1 over 2 square root of beta 2 g plus delta times eta, which is just the bound we got before, right? So this is this bound here. And plus 2 eta sigma squared over delta bt g 1 minus beta 2. So what is this? This is just this here multiplied by 1 over delta and 1 over bt sigma squared. So now notice that we're almost done, right? Because now remember, to a stationary point, for a stationary point to happen, we need that the norm of the gradient to be less than some epsilon, right? And we need that to go to 0 as the number of iterations grow, so we converge to a real stationary point. Right, so now let's realign this equation. So we just take the gradient to the other side and we take the expectation to this side, and now I can write it in this way. So all I've done is I've taken this to the left-hand side and got the expectation to the right-hand side. So taking this to the left-hand side will give me this. Less than will stay the same because I'm not multiplying and dividing or anything. I'm just adding, subtracting, and I'm just doing so I'm just reassigning this inequality, and then I'll get minus e of L theta t plus 1 given theta t plus this term which remains unchanged. Good. Now, as we said before, we have been so far studying the randomness given some theta t. Right? So given some theta t, we've been studying how the objective value changes between two successive iterations. All that is good, but what we really need to understand is what happens over the total randomness we induce in our algorithm. So what happens when we have the total randomness and not just this given theta t randomness? So to do that, we just apply the total expectation. So E total is E over all the randomness induced in the algorithm on both sides of this inequality. So this is a constant, so it stays here, nothing changes. And now here we will have E total of the norm of the gradient, which is less than E total of the L theta t minus E total of L theta t plus 1. So where did this come from? Well, from the rule of total expectation. E total of a conditional expectation is just E total, and that will give me E total. Then I divided by eta here, so there was eta here, I divide by eta, and this remains unchanged. All right. So now remember that what we do is we run our algorithm from 1 to t. Right? So what we do is we run our algorithm from 1 to t. Right. So we have like over time from 1 to t, that's how many iterations we do. So in order to understand what happens with our gradient, what we're gonna do is we're gonna sum over time from 1 to t and see what really happens in this equation, right? So we take the summation from 1 to t on the left hand side and on the right hand side. So on the left hand side, this is there, and on the right hand side for this equation right here, it's kind of a harmonic series, right? Because remember, it's theta t minus theta t plus 1, so it's like 1, 2, then 2, 3, so 2 and 2 cancel out, and therefore you're left only with the first and the last terms, right? So it's kind of like the first cancels with the first stays, the second cancels with the second, and the t minus 1 cancels with the minus 1 cancels with the t minus 1, and then you're left with theta t plus 1. So sorry, I said harmonic. I think this is called telescopic series, and then they just cancel out. Right, it's not harmonic, sorry, it's telescopic. And then we have this division by 1 over eta t, and now don't forget that we have the summation as well here of 1 over bt. Good. Now remember that the theta 1 is in our choice, right? Like we can choose theta 1, so it's not really random, and that's why E total of L theta 1 is just L theta 1, because there's no randomness from the algorithm that induces theta 1, it's just something we pick. And now remember that the function we have, right, is always bounded from below by like a global minimum, right? So we assume that there exists a global minimum. So that means that the loss function value or the objective value is minimal at the global minimum, right? And that's why now what you can do is you can rewrite that E total L theta t plus 1 is greater than L of theta global minimum, and that's why minus that is less than global minimum minus L of global minimum, and that's why we get this equation here. And because we want to understand what happens on average over these iterations, we further divide this bound by t, so you have 1 over t everywhere. Now you can see we're getting really very close to the end here, because on one side we have the expected norm of the gradient squared, and that means that if we are able to randomly pick one theta from batch of thetas we created so far, then in expectation the average behaves like this, right? So that's what this equation is really saying. Good. So now what we're going to do is we need this term to be less than some epsilon, right? Remember, our stationary point is that the norm of the gradient should be less than epsilon. Agree? So since the norm of the gradient is less than epsilon, then we have a c here, right? Don't forget the c here. And that's why we want this to be, the right-hand side, to be less than epsilon c1. Because if you divide by c1, then that means that the average expected norm of the gradient is less than epsilon, and that's great. That means we're getting to a stationary point. So now with that, oh, right, so sorry, I forgot to mention that I just simplified things because these are constants. So I called this to be c1, and I called this to be c2, right? So I just simplified things, just not to write them over and over again, because they're constants, they don't matter much. Right. So now we agreed that we need the right-hand side of this equation to be less than or equal to epsilon times c1, which means that we want the L of theta 1 minus L theta global over t times eta plus C2 to be 1 over T summation of 1 over BT to be less than epsilon times C1. And now, as you see, C1 and C1 will cancel out, which means that the average norm squared, expected norm squared will be less than epsilon. Good. So now what we're left with is to see what happens, like how much T we would need, like how many iterations we would need in order to achieve this, and what happens when we consider different regimes for the batch size. So for now, let us say that the batch size, we're going to choose it to be a constant, right? So we're going to say BT is equal to B, right? So we're just going to choose this to be a constant. And now remember that the sum of these two needs to be less than C1 epsilon. So we're going to make this to be less than half of that, and this also less than the other half, right? So in order for this to be less than half of that, if we pick B to be 2C2 over C1 epsilon, we can show that C2 over 1 over T, the summation of 1 over BT, which is just this term here, will be less than C1 epsilon over 2, which means it's less than half of this term here. And now we need the other term to be also less than half. So for the other term to be less than half, we need to choose T to be this equation here, which is just an order of 1 over epsilon, really. So with that, this amounts to being less than half of this, and this first term amounts to be less than the other half, and therefore the sum is less than the C1 epsilon. So with this, if we pick BT, like the batch size to be this, and the total iterations to be C1 epsilon over 2, then we can say that the total expected average of the norm of the gradient is less than epsilon. Right, so that's great, because this shows that if we subsample something randomly from all the iterates we created, then in average the expected norm of the gradient will be less than epsilon, which means it's an approximation to a stationary point. But here's the problem. The problem is that if we increase T, this will never go to 0. And the reason is because this is a constant. So because the batch size is a constant, even if we make the limit as T goes to infinity of this equation, we will never ever reach to 0. We will reach to C2 over C1 B is not equal to 0. And the reason for that is also clear from this equation here, right? Because this term here will definitely go to 0 because it's like a constant divided by T. If T becomes like infinity or it approaches infinity, then the limit becomes 0. But now with this term here, remember that 1 over BT is a constant B. So now you have 1 over B plus 1 over B T times, which is T over B. And T cancel out, so you will get something that is a C2 over B. And now the problem is that with that, this will never vanish, even if you give it infinite time, infinite big T, it will never diminish to be 0. And that's why what this shows, if you have a fixed batch size, you will actually get to an approximation of a stationary point, but you will always have a constant error. So how can we remedy that? Well, here's the last part. In order to remedy that, what we're going to do is we are going to pick the batch size to increase with time. So what we're going to do is we're going to make that batch size to be some function of T. So it's like this, the integer value of C2 over C1 times T. And now what will happen is that if that's the case, then this 1 over T summation 1 over BT will behave like ln T over T plus gamma, and that gamma just comes from the divergence of this harmonic series 1 over T. And now what will happen is that as T goes to infinity, then ln T over T goes to 0, which means that we still get an epsilon stationary point if we chose our T to be in the order of 1 over epsilon. But what's cool now, if you grow your batch size, let's say in this function of time, then the norm of the expected, of the average expected norm of the gradient squared will go to 0, which means we will converge to a stationary point. So if we give it infinite time by these choices, if you make the batch size increase, then you actually converge to a stationary point. Woo! That was a very long math derivation, but now you know how to prove Adam. and how you prove the convergence of Adam. So remember what we've done. We started from the property of L smoothness. We replaced the equations. We realized a ratio of random variables. We added subtracted terms. Then we bound the absolute values. Then we plug it back in. Then we realized that we need to bound the third term, so we introduced assumptions. So we had 3 assumptions, right? And these assumptions were that the subsampled loss function is L smooth, and the gradient is upper bounded by a G. And what was the third assumption? And we made a third assumption on the variance, right? So we said that the variance is bounded by sigma squared, which allowed me to bound at the end the norm of the expected norm of the gradient squared. And we also gave you an exercise to prove that, prove how we can get from, so the exercise is going to be here. And we would really like to see your answers to that. We asked to go from this to this, right? So how can we go from that to that? Please have a look at that, and then we can look at your proofs in the comments below. You can also write us emails in case you want to have a discussion over this. All right. So this is Adam, and we might have part 3 about the coding part of these algorithms and comparing Adam to others. But before doing that, what we're going to do is we're going to issue a poll in order to have voting on what topics you would like to hear about next, because we really want to deliver what you would like to hear about. So this was the first on the optimization series. Thanks a lot. If you like what you saw and you appreciate the effort we put in, please subscribe and like this video and share it in the community as well. Thanks a lot. Thank you. See you soon.